Namaste students, welcome to Rama Teaches You. Today we are going to do the second video on the IB Physics chapter E1. Okay, structure of an atom. Okay, in the previous video, we had discussed about the Rutherford's scattering experiment where he used alpha particles and a gold foil to show that atom was almost empty. All the mass of an atom can be assumed to be concentrated in a very small portion inside the atom, which we call the nucleus. The nucleus is positively charged. Okay, it contains protons and neutrons. That's why they are called nucleons. And the electrons are revolving around the nucleus of an atom. Today we are going to do the remainder of the chapter. Okay, let's actually study what is happening here now. Mm, okay, let's start. So, how is the distance of closest approach calculated using conservation of energy? Okay, conservation of energy means what? Energy can neither be created nor be destroyed. Understood? Energy can neither be created nor be destroyed. Now, what is the distance of closest approach? Now, you may be thinking in your head that these alpha particles they actually touch to the nucleus, and then because of that they had to come back. They collided with the nucleus and then they were repelled. But then you might be wrong. Okay, the alpha particles is not actually hitting the nucleus and then coming back. There is a electrostatic force of repulsion that is taking place between the alpha particle and the nucleus. Now, why did I say electrostatic force of repulsion? As we know, we have already studied the electrostatic force, right? The force that exists between two charges is called an electrostatic force. Now, the alpha particle is a charged element, right? Alpha particle is charged. It has plus two positive charge, units of positive charge. The nucleus is also a positive element. No, not an element, a positive substance. So all in all, when the alpha particles comes in close contact to the nucleus, it gets repelled due to the positive repulsions. Now, what is happening here? The alpha particle is not simply dropped next to the gold leaf. It is accelerated. It is accelerated and it is thrown straight into the gold leaf. Okay, when it is accelerated, it has a certain amount of velocity. Okay, we have seen that uh, a charged particle, okay, it accelerates when it goes through an electric and magnetic field, right? So you have an alpha particle, you have placed it in an electric and magnetic field, due to which what happens? It gets accelerated to a certain velocity. It may have had zero or very less velocity in the beginning, but after a while it is accelerated and you make it reach to a final velocity. Okay, and final velocity is what gives the alpha particle the kinetic energy required to move. Okay, kinetic energy is the energy of motion. So the alpha particle is initially given a kinetic energy, and this kinetic energy is allowing the alpha particle to go very near to the nucleus. Okay, now let's actually discuss what the theory is saying. The data from the Geiger-Madsen-Rutherford experiment can give an estimate for the diameter of a gold nucleus. Figure 10 shows what happens when an alpha particle is scattered and exactly reversed in path. It must originally have been heading straight for the gold nucleus. In other words, on a head-on collision. But does the head-on collision actually take place? No, the head-on collision does not take place. Now, think of it this way. Think of a spring which is next to the nucleus of the of the gold atom. A ball is being thrown and is moving with a very high velocity, thus having a very high kinetic energy. When that ball hits the spring starts to compress. Okay, the string starts to compress. Thus, all the kinetic energy of the spring is all the kinetic energy of the ball is getting transferred into elastic potential energy and it is compressed in the spring. Okay, similarly, what is happening here? The kinetic energy of the alpha particle is converted into electrostatic potential energy and is stored inside the alpha particle. Now, because all the kinetic energy is being converted into electrostatic potential energy, the alpha particle does not have any more kinetic energy left, therefore it stops. That is the distance of closest approach that the alpha particle can have. So as the alpha particle approaches the nucleus, the initial kinetic energy K E alpha gradually transfers to electrostatic potential energy. When the alpha particle sorry, when the alpha particle is at its closest point to the nucleus, it stops moving just for an instant. Its kinetic energy is zero here. So it has not actually touched the gold atom. It has just converted all its kinetic energy into this repulsive potential energy. This is the distance of the closest approach RC, and we take RC as the estimate for our upper limit of the nuclear diameter. Okay, so how much closer can you go to the alpha part, to the nucleus's to the atom's nucleus is what gives us the nuclear radius. Okay, so how close can you be? Okay, so basically the closer you are, that means you have not reached the radius of the nucleus. Okay, the maximum closeness will give you an approximation of how big the nucleus of the atom is going to be, the nucleus of the gold atom. If it were very far away, then the nucleus would be big. But when as you increase the kinetic energy, you are becoming closer and you are getting closer and closer and closer to the nucleus. Okay, so this gives us an estimate of what the nuclear radius is going to be. Okay, thus this is the distance of closest approach RC, and we can take RC as the estimate for the upper limit of the nuclear diameter. The positive alpha particles is then repelled by a positive nucleus, and it is reversed in direction. So that is what is happening here. The alpha particle was initially going here, 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 then it went closer to the nucleus, it lost all its kinetic energy, it stopped, and now it is coming back. Understood? Okay, next. When the alpha particle has come to rest, all of its initial kinetic energy, Ke alpha, has been transferred to electrostatic potential energy, and therefore we can say that half mv square, which is the formula for kinetic energy, becomes equal to K Q of gold upon Rc. We know that the electrostatic potential energy's formula is E is equal to K Q1 Q2 upon R. Okay, this is the formula for potential energy. Okay, K Q1 Q2 upon R. Now, here Q1 is what? It is the charge of the alpha particle. Q2 is what? The charge of the gold nucleus. Okay, and R is what? It is equal to RC. It is a distance, the closest distance possible between the alpha particle and the nucleus. Clear? And we know what E is, right? E is 9 into 10 to the power 9. Okay, Newton meter square per Coulomb square. So this is what the Coulomb's law. Do you remember Coulomb's law, from where we had the value of K? Okay, now this will become equal to the half m alpha v alpha square. M alpha is what? The mass of the alpha particle. V alpha is what? The final velocity to which the alpha particle was accelerated. Okay, the final velocity to which the alpha particle was accelerated. Now, RC is called the closest approach between the alpha particle and the nucleus. When E alpha of the alpha particle is equated to the electrostatic potential energy RC, then what do we get? E alpha is equal to KZE multiplied by 2E upon RC. Now here Z is what? Z is the atomic number for gold. Okay, atomic number gives you what? The number of protons. The number of protons multiplied by the charge of each and every single proton gives you the charge of the nucleus. The number of protons multiplied by charge of each proton gives you the charge in the nucleus. And we know that helium has two protons in its nucleus, right? Therefore, you get 2e. So K Ze multiplied by 2e upon Rc. This is the distance of closest approach that we have. Clear? Okay, let's move on. Now, where K is the Coulomb's constant, Z is the atomic number of protons in the gold nucleus, so that the positive charge of the nucleus is Ze and 2e is the charge of the alpha particle. You should be able to recognize the origin of this equation from D2. We have already discussed this potential energy, electric potential, and all the other stuff. When the equation is rearranged to make Rc, you get what? Rc is equal to 2kZd square upon E alpha. Okay, from the data, the Geiger-Madsen-Rutherford experiment, Re alpha is equal to 7.68 mega electron volt. So the alpha particle was having a very high kinetic energy. Okay, and the value of Z is 29. So when they put all the formulas, when they put all the values in this formula, they got the distance of closest approach to be how much? 3 into 10 to the power minus 14. Okay, 3 into 10 to the power minus 14 meters. Rutherford's theory makes several approximations, which means that it can only ever be a rough estimate of Rc. It is not the actual value. The nucleus radius is not this. Okay, but it is close to this, we can say. Now, the gold nucleus is regarded as a point mass that does not move. In fact, it must be repelled by the approaching alpha particle. That is, it is called a recoil. One second. So, we assume that the alpha particle does not penetrate the nucleus. At small values of Rc, an alpha particle is influenced by other nuclear forces, not just the electrostatic repulsion. Okay, now research since Rutherford's time shows that an attractive strong nuclear interaction operates at small distances within the nucleus. Now, this is known as the nuclear force. Okay, the nuclear force is the force which holds the protons together. Okay, now the nuclear force has to be stronger than the electrostatic repulsive force, then and only then the nucleus will be formed. Otherwise, the nucleus cannot be formed. Okay, so this complicates the analysis. Because this strong nuclear force is attractive, it reduces the effect of the electrostatic repulsion. That means what? When the alpha particle is brought very close to the nucleus, instead of repelling it, a new kind of force is getting involved. So here Rutherford did not take this force into consideration. He was only interested in the electrostatic repulsive force. But when you are very close to the nucleus, a new kind of force called the strong force or the nuclear force actually comes into being. And this nuclear force is stronger than the electrostatic repulsive force. So if you bring the alpha particle very close to the nucleus, instead of repelling it, it will actually attract it towards the nucleus. Understood? So this could lead to some slight discrepancies in the nuclear radius. Okay, now what else? There is more details about the strong nuclear interaction in topic E3, where we will actually discuss the structure of a nucleus. It's a very interesting chapter. Now, deviation from Rutherford's scattering. Okay, let's actually read this. It's just one page long. Okay, deviation from Rutherford's scattering. At high initial kinetic energies E alpha of the alpha particle, the closest approach distance Rc becomes smaller. The more kinetic energy you have, the closer you can go into the nucleus. Am I right? The more kinetic energy you have, the more closer you can go to the nucleus. A large kinetic energy will lead to an impossibly small nuclear diameter. However, when very energetic alpha particles approach the nucleus, There comes a point where the scattering no longer obeys the assumptions Rutherford made. Okay, when you are very, very close to the nucleus, a new kind of dynamics is happening. Okay, so ideally speaking, the predictions were supposed to be like this. Okay, so as the initial kinetic energy increased, the intensity of the alpha particles angle should have decreased. But this is not what happening here. There is a slight deviation from the actual norms. Okay, now, so this observation or the observations of this behavior was made in 1961 by Iceberg and Porter, who used a lead 208 target. They showed that for alpha particles of initial kinetic energy greater than 28 mega electron volts, the predictions of Rutherford's equations were no longer maintained. You should think the kinetic energy as being a largest energy for which the scattering will still obey the Rutherford's model. Then the estimate gives the smallest RC at which other nuclear forces do not operate. This is the effective size of a nucleus. Okay, so what is the effective size of the nucleus? The effective size of the nucleus is the distance of closest approach where the Rutherford's models are not violated. Okay, the if you reach a region in the nuclear space where Rutherford's models are violated, then what happens? The whole model fails. Clear? The whole model fails. Is this 100% clear? Okay, so what is the actual diameter of the nucleus? It is equal to the distance of the closest approach when alpha particle with a kinetic energy, with a large kinetic energy, is still able to obey the Rutherford's laws. Okay, if the Rutherford's laws start failing, then you are very close to the nucleus. You are very close to the nucleus, and therefore that won't be considered as the nuclear distance. Okay, clear? Okay, now next, the nuclear density. Now we now know that the total number of nucleons inside the nucleus include both protons and neutrons. Rutherford and his co-workers knew about protons, but it was not until 1932 that neutrons were finally identified. This took many years because the neutrons is uncharged, and most research techniques early in the 20th century relied on the effects of charge and the ionization it caused to make measurements. They were only able to make measurements of charged particles because that was the constraint at that time. Only particles with such this thing could be measured. With charges could be measured. Now, it is possible to arrive at a simple equation that relates the radius of the nucleus to the total number A, that is what the mass number, the atomic number, the number of nucleons. Okay, A of nucleons inside it, the nucleon number. The nuclear volume V must be proportional to the total number of nucleons, as the volume is directly proportional to A. Okay, the as the number of nucleons increases, the size of the nucleus also increases. Now we know that in the nucleus, the nucleons between the nucleons, there is hardly any space between them. Think of it this way: you've seen M&Ms, right? So in a glass container, okay, you have a transparent glass container in front of you. If you have less number of M&Ms in them, then the volume occupied by the M&Ms in the glass container will be less. If you pour in more M&Ms, what happens? More volume is being used by the M&Ms. Okay, so this is what they're trying to say. He is trying to say that the alpha particles, sorry, the number of nucleons, as the number of nucleons in the nucleus increases, the volume of the nucleus also starts to increase. So when we assume that the nucleus is spherical, okay, when we assume that the when we assume that the nucleus is spherical, then volume is equal to 4 by 3 pi r cubed as usual, and r cubed is directly proportional to A. So we know that volume is directly proportional to the number of nucleons. Therefore, 4 by 3 pi r cubed is directly proportional to A. So can I say that R cubed is directly proportional to A? Because 4 upon 3 pi is a constant. So R cubes becomes proportional to A. Okay. Now, this is more usually given as R is equal to R is directly proportional to A to the power 1 by 3. So we can write R is proportional to the cube root of A. Clear? Now, to remove this proportionality sign, we have a constant R is equal to R naught A to the power 1 upon 3. Okay, so this is known as the Fermi radius. Okay, and this Fermi radius is equal to what? 1.2 into 10 to the power minus 15. Okay, that minus 15 is known as a Fermi. Okay, a Fermi radius. 1.2 into 10 to the power minus 15. This analysis can go one step further because of the earlier equation for the nuclear volume can be written as V is equal to 4 by 3 pi r cubed. So instead of r cubed, you can write r naught a to the power 1 by 3 the whole cubed. So r cubed becomes r naught cubed a. So the volume becomes 4 by 3 pi r cubed is equal to 4 by 3 pi r naught the whole cubed multiplied by a. So this is the volume of the nucleus. Okay, so this leads to an estimate of the density of the nucleus. Now, what is the formula for density? Density is equal to mass upon volume. Okay, density is what? Mass upon volume. The mass of the nucleus upon the volume of the nucleus. Now, mass of the nucleus is what? A, number of nucleons multiplied by mass of each nucleon. What is the mass of a proton, Akshay? 1.6 into 10 to the power minus 27 kgs, and this is similar to the mass of a neutron also. Mass of a proton and mass of a neutron are very much similar. So I can write it as 3u upon 4 pi r naught cubed. Okay, thus 3 has gone upwards. Next, now the A has been cut off. This is something that is very, very important for us to realize. Okay, because the density does not have an atomic mass term, therefore, the nuclear density will always remain constant no matter what atom you have. That is, the nuclear density of an atom, a small atom, say lithium, will be the same as the nuclear density of a large atom like uranium. Both will have same densities. Their mass won't be the same, their volume won't be the same, but their densities will surely be the same. Okay, understood this? Okay, the quantity U in this equation is known as the unified atomic mass unit, and it is roughly equal to the mass of a neutron or a proton. They are not quite the same. 1 U is equal to 1.6 into 10 to the power minus 27 kgs. These data give us a nuclear density of 3 into 1.7 into 10 raised to the power minus 27 upon 4 pi into this value, which gives us an equation of how much? 2.4 into 10 raised to the power 17 kilograms per meter cubed. So it is very, very heavy. If you have a nucleus, if for example, if you have 1 kilogram, if you have 1 kilogram of nuclear material, okay, it will be a huge value, very, very massive. 2.4 into 10 to the power 17 kgs. Okay, understood? Akshay, do you know what the mass of Earth is? 6 into 10 to the power of 24 kgs. Okay, now 1 kg, 1 kg of neutron is how much? 10 to the power of 17. That is basically you have 17, 18, 19, 20, 21, 22, 23, 24. That is approximately 10 lakhs. Yeah, 10 lakhs. Okay, 10 lakh kgs of neutrons. 10 lakh kgs is nothing. Okay, 10 lakh sorry, wait, hold on. No, my calculation. This is the density, right? Uh, Somewhat like that. I am confusing myself. Okay, it's a huge number. Now, let's actually discuss whether such a object exists. So, in the sky, there is something known as a neutron star. Okay, this is where the gravitational forces of the star just simply crush the whole atom and remove all the spaces between the atoms, and they become condensed to a very large extent. For example, just imagine the size of the sun getting crushed into size of that of, let's say, Manhattan, the whole Manhattan island. Okay, the whole mass of sun got crushed and it is now compressed to the size of a small island in the United States. Okay, now what is happening here? The double star system X7 contains a neutron star thought to have a mass of 1.4 times the mass of Sun and a radius of 11 kilometers. 11 kilometers means what, Akshay? It means approximately like uh, 11 kilometers is nothing. 11 kilometers is just distance from one part of Delhi to another part of Delhi. That's it. It's smaller than Delhi. The whole size of the sun crushed, mass greater than the sun, 1.4 times greater than the sun, crushed to a very small ball. Okay, this large density is a result of the gravitational collapse of a massive star. Okay, now the energy inside this combustion is what's allowing the star to exist in this, our star to exist in such volumes. But eventually, what will happen? All the hydrogen will eventually get converted into helium. Okay, and then helium will get converted into heavier and heavier elements till it reaches iron. Once it reaches iron, it can no longer have that much energy to compress it much further. Therefore, it will collapse into its own gravity. An apple made of nuclear matter would have a mass of about 10 to the power 14 kgs. This is about 1,000 times larger than the total mass of all humans alive on it. One single apple would weigh 1,000 times the mass of all humans on earth. Okay, so now, the interesting thing is that because the nuclear density does not depend on the atomic mass, the nuclear density will become uniform throughout the periodic table. Whichever atom you choose, the density of the nucleus will remain the same. Understood? The density of the nucleus will remain the same. Now, this density is the same for all nuclei since this was the original assumption. The interaction between the nucleons are repulsive at short distances, and so the nucleons cannot penetrate each other. Understood? One nucleon cannot go inside another nucleon because of the repulsive forces that exist between them. Okay, it's like a billiards ball. Okay, have you ever, when we start playing pool or billiards, what do? We place all the balls inside that triangular scale, right? So that we can arrange them. When that arrangement is made, one ball does not take place of another ball. They are tightly packed with each other. There are small gaps between them due to the repulsion, but they cannot overlap each other. They cannot superimpose each other. Okay, so we can say that if the whole table is filled with these balls, okay, the density of the balls per unit volume will remain the same. Okay, because one cannot overlap the other. Now, next, mm, we can actually skip this. Okay, we can skip this and we'll go to the my favorite section, the emission and absorption spectrum. Okay, this is actually pretty fun. Now, we know that according to Rutherford's model of an atom, okay, no, not actually Rutherford's, the Bohr's model of an atom. Now, Bohr said that electrons revolve around fixed orbits, okay, called stationary orbits around the nucleus of an atom. Okay, they revolve around the nucleus of an atom in fixed stationary orbits, and when they do revolve around these orbits, they do not lose any energy. But if an electron were to absorb some amount of energy in the form of heat, light, or electricity, it would increase its energy. Now, we know that a particular orbit can only sustain an electron with a certain amount of energy. If the electron's energy increases, then it has to go into a higher energy orbit. Okay, there are various orbits around the nucleus of an atom. Okay, and each orbit has a fixed amount of energy which the electron must possess to stay in that orbit. If the electron gains some additional amount of energy, what happens? The electron is now excited to a higher energy level. It jumps from a lower energy level to a higher energy level. Okay, understood this? Any doubts here, Akshay? Okay. Now, by the early, yeah. Now, let's actually see what's happening here. By the early 19th century, scientists understood that sunlight had a collection of spectrum, but the reason for it were unknown. We know that sunlight is made up of seven different lights, right? Seven different colors that are visible to the human eye. That is the violet, indigo, blue, green, yellow, orange, and red. There are other colors also present inside the sunlight. We cannot see them. Like we have the infrared light, the ultraviolet, the radio, the cosmic. All of these rays are actually present in the sunlight. But unfortunately for us, we cannot see them. Okay, so in 1802, William Wollstone observed some strange dark lines in the sun's spectrum. He see, you cannot, whenever you observe the sun's light, you see a continuous spectrum. Always. You will always see a continuous spectrum. But what he observed was one day when he was looking at the photograph of the spectrum that he had taken, he observed that some of the lines were missing. Okay, now, but it took a further 12 years before Joseph von Fraunhofer invented the diffraction grating and was able to observe these dark lines in detail. See topic C3, page 432. We now know the discovery Fraunhofer lines is an absorption spectrum. We shall see how these lines are formed later. So, I'll just give you a brief understanding. Now, we know that light is made up of energy. Okay, light is made up of energies. Now, different radiations have different amount of energies. Okay, different radiations have different amount of energies. Now, there are some electrons present inside the atom which are looking for certain energy levels. Think of it this way. There is a person pushing a snack tray. Okay, there is a person pushing a snack tray, and all the students are in a straight line. Okay, they are doing their homework or something like that. But when the snack tray goes through them, okay, they basically select certain snacks that they like. Okay, you being a vegetarian, you would not take something that has egg or any other non-vegetarian material present in it, right? You will try to take snacks that are for your liking. Okay, you would not take something that you don't like. Similarly, if you provide an electron with all sorts of energies, it will only absorb energy that it wants. Okay, that it is allowed to. Okay, so light is made up of energy, light is falling on an electron, the electron is absorbing some radiations or some spectral lines, okay, which it is using to excite itself. These are the missing lines that Fraunhofer basically observed while he was conducting this experiment. He saw that some electrons, have taken some energy levels from this huge spectrum, which caused it to have dark lines in between. Are you able to follow me, Akshay? Okay. Now, so it's like this. You have a chocolate tray. Okay, someone is pulling a cart that has a lot of chocolates in it. Now, when you are taking this chocolate tray through you, what happens? Some of you will take some chocolates, some of you will take other chocolates, but still there will be some chocolates remaining in the tray, right? That is the spectral line that he's observing. Okay, that is the image that he's observing here. So the colors that he's able to visualize are the colors that are left behind. The dark lines are the light sources that the electron has absorbed. This is known as the absorption spectrum. Okay, when a certain radiation passes through an element, the electrons that are present in the element will absorb certain wavelengths from the spectrum, thus causing dark lines to appear in between a colorful background. Dark lines appearing behind a colorful background. Okay, this the technique for observing spectral experimentally is to produce light by passing an electric current through a low pressure gas or by heating a substance so that it produces a flame. Okay, the technique for observing spectra experimentally is to produce light by passing an electric current through a low pressure gas. Do you remember the cathode rays, where you passed electricity through the gas, resulting in the formation of some amount of light that was coming out? Similarly, when you throw some gunpowder or metal flakes on a flame, okay, iron will not produce a flame. But if you grate that iron into a powder and you just simply sprinkle some amount of that iron powder on top of an open flame, it will catch fire and it will produce various different colors of lights. Still following me? Okay. Do you want to say something? I think you want to say something. Exa- yeah. Oh, exactly. Yeah. Now, Akshay, when we burst crackers during Diwali or some celebrations, yeah, different colors are observed, right? The different colors are the different metal compounds that are powdered, and basically they are heated up. And when they are heated up, they produce these various different colors. You know what is happening there? Huh? Exactly, exactly. That is what the whole principle of firecrackers was, basically this phenomenon. Okay, the ancients in India and China, these people realized that they could produce different colors of flames. Okay, they could produce different colors of flames when they heated the metal over an open flame, and that is the reason why firecrackers and gunpowder and all this stuff was produced here locally. in the Asian subcontinent is where this initial discovery took place. Okay, the atoms then emit electromagnetic radiation. So light has not fallen on them. They got their energy from heat, air, electricity. When they absorbed heat and or electricity, now they are emitting a radiation outside. They are emitting some amount of radiation outside. When this radiation is incident on a diffraction grating or a prism, it becomes diffracted by the grating or dispersed by the prism into separate wavelengths. These leave the grating or prism at different angles to the original direction of the radiation. So why are we using a prism? We are using a prism to separate the various colors of light that are being produced by the electron. Okay, so that we can study what are the wavelengths of light that were absorbed, what were the wavelengths of light that were emitted. Okay, so what did you do? You heated an atom, or you passed the atom through an high intensity current. Okay, high current in its gaseous phase. Through both these mechanisms, you were able to excite the electrons inside the atom. The excited electrons absorbed this energy and then went to a higher energy level. Okay, they were in the excited state, but they could not remain in that excited state for a long time. So what did they do? They came back to their initial ground state. But to come back to their initial ground state, they had to release the energy that they had absorbed. And the only way the atom knows how to release the energy is in the form of radiation. So, when the excited electron, which got excited in the first place by heat or electricity, when it goes to the excited state and comes back, it releases radiation. It releases the excess energy that it had absorbed in the form of radiation. And this radiation contains colors of light of various different wavelengths. It could contain some red light, blue light, green light, violet light. Now, you are using a prism to separate or basically disperse the light into their respective wavelengths. You are dispersing the light that was produced into separate wavelengths. Okay, now they can then be observed using a telescope or by allowing the light to fall on a screen. Do you observe this one? Okay, here, see, this is the emission spectrum. Okay, the light is now falling on a screen, a dark screen onto which the light is being formed. Now, you observe what? You observe colors behind a dark background. This is called the emission spectrum. Okay, now absorption spectrum and emission spectrum are negatives of each other. In the absorption spectrum, what was happening? You are observing dark colors, dark lines on a colorful background. In the emission spectrum, you are observing colors in a dark background. Okay, now if you take the absorption spectrum of one element and the emission spectrum of the same element, and then you place them one on top of each other, you will again get a continuous spectrum. See, an element can only absorb certain wavelengths. An element can only emit those same wavelengths when it is excited. Okay, so it's like this. You had a tray filled with chocolates in front of you. You took one or two chocolates. Now, I'm asking you to put back the same amount of chocolates. So, you taking the chocolates from the tray was what? Was an example of the absorption spectrum. You putting back the chocolates into the tray is an example of an emission spectrum. So, when both these activities, the absorption and the emission, are taking place, when you place one on top of each other, you again get a tray filled with chocolates. You get the continuous spectrum once again. Do you want me to explain this a little bit better? If you want, because I know it's a hard topic. Okay, so what happened in the beginning? when the absorption was taking place. These are two different experiments, Akshay. I'm just trying to correlate these two experiments. These are two different experiments. In the absorption spectrum, the element is absorbing certain wavelengths of light to excite its electrons. In the emission spectrum, the electron that is excited due to the heat and electricity, when it is coming down, it is again releasing the same amount of wavelengths outwards. Okay. Yes, exactly. They are negatives of each other. You know what a negative is, right? Basically, when you take a photo in the olden cameras, you used to have a negative of the film. So whatever this thing you had to develop it to develop colors. Okay, so they are photo negatives of each other. Now, every element has a certain picture. If you observe the absorption or the emission spectrum of an element, you will observe that different elements have different pictures. Okay, different elements have different pictures. Now, with this information, what have we done? We are now able to observe what all elements are present inside a certain material. We were able to take this information and go to Mars and observe the soil of Mars and see what all elements are present in the soil of Mars. This is known as spectroscopy. A spectroscope is a machine or a device which does this analysis. Okay, by putting a small sample of whatever you want to record inside a spectroscope, it gives you an information. There is this much amount of hydrogen, this much amount of lead, this much amount of gold, this much amount of carbon. Okay, so it gives you a whole analytical picture of what all elements are actually present in it. Clear? Okay, now the continuous spectrum of the sun is caused the continuous spectrum of the sun is caused by the interactions of all the atoms in the hot dense gas at the sun's visible surface. As the pressure of gas decreases, however, the visual appearance of the spectrum changes dramatically. The individual atoms interact less and less and as the pressure falls until at low pressure the spectrum forms a single element because of a series of separate uh, for a single element becomes a series of separate discrete lines. Okay, again I'm going to repeat this. The continuous spectrum of the sun, this is the continuous spectrum. Okay, Akshay, the continuous spectrum here. The continuous spectrum of the sun is caused by the interaction of all the atoms in the hot dense gas at the sun's visible surface. Okay, all the atoms in the surface of the sun are getting interacted, or basically they're getting excited, due to which what happens when they come back, they will release certain amount of radiation as the pressure of the gas decreases. However, the visual appearance of the spectrum changes dramatically. Okay, the atoms interact less interaction is taking place. As you move further and further away from the center of the sun, the pressure gradually decreases. There is much less interaction. The In the core of the sun, the interaction is extreme. There is extreme pressure. But as you move towards the surface of the sun, the pressure that is being exerted on the atoms of the sun is slowly and slowly decreasing. Okay, as the pressure falls until at low pressure, the spectrum for a single element becomes a series of separate lines. Okay, the for a single element you get different series of lines. Okay, so here see, the line spectrum for hydrogen is the first one, for helium is the second one, and for mercury is this. So you can think of it as a fingerprint, which can be just like fingerprints are used by the police to actually find the criminals. You can use the fingerprint, the colorful fingerprint, given by these elements to distinguish what they are. Okay, now, so the line spectrum extends. Wait, the low pressure spectrum is known as the emission line spectrum and is a characteristic of elements that is producing it. Now, why do we call this a characteristic? Because these emission spectrums can be used to identify the elements. Okay, if you have an understanding, if you, we know a lot of elements, right? We know 118 elements in the periodic table. Now, if we do the emission analysis of these 118 elements, we can basically use it as a database. Okay, just like the police has a face of all the criminals that they are looking for in their database, we have the fingerprints of all the elements in our database. So if we analyze an element in anywhere around the universe, we can identify what all atoms and molecules are present in that material. Right? Now, figure 14 shows the line spectrum for three different elements. The color arrangement of the lines are different and unique for each and every single element. Each and every single element will produce its own colors at different positions. Okay, just like every human being has a different fingerprint. Okay, similarly, they have different spectrums. Now, the line spectra extends beyond the visible range of light. For hydrogen, an atom that consists of one nuclear proton and a single electron outside the nucleus, there are six series of lines that have been extensively studied. We call it the emission line spectrum. They are basically they're named after the people who discovered it. Okay, you have the Lyman, you have the Balmer, Lyman series, Lyman, Balmer, Passion, Brackett, Humphrey. Okay, okay, these are Lyman, Balmer, Passion, Brackett, Lyman, Balmer, Passion, Brackett, Lyman, Balmer, Passion, Brackett, Humphrey. I think I'm missing a scientist's name. Just hold on one second. Again, the Lyman series, the Balmer, Lyman Balmer Passion, Brackett, Fund, and Humphrey. These are the six scientists that discovered the six emission spectrum of hydrogen. We know that the emission spectrum, so including one in the ultraviolet region, one in the visible region, and the and two in the infrared region. Okay, now we know that there are various different energy levels around the nucleus of an atom. There is the ground state, first excited state, then second, then third, okay, then fourth, then fifth, then sixth, and it goes all the way up to infinity. Okay, so these are the various energy levels that exist. Okay. Now the Lyman series says that if an excited electron falls to the ground state, if an excited electron falls back to the ground state, the light that it will release will be an ultraviolet light. That is the Lyman series. If an excited electron falls onto the first state, it is called the Balmer series. Okay, it will release light in the visible spectrum. Then, if a light falls onto the third energy level, that is the second excited state, it's called the Passion. And then the fourth will become Brackett. Then the fifth will become Fund, and the sixth will become Humphrey. Okay, so the Lyman series, that is, if an electron falls to the ground state, it produces ultraviolet radiations. Okay, if it falls to the first state, it produces visible. Then you have the infrared. This also is infra. This is infra. This is far infrared. Okay, these are the emission spectrums that we are going to study. Okay, so the line, again I'm repeating myself. Okay, The line spectra extends beyond the range of the visible region. For hydrogen, an atom that consists of one nuclear proton and a single electron outside the nucleus, there exist six series. What are they? Lyman, Balmer, Brackett, Paschen, Fund, Humphrey. Okay. I may be making mistakes in their names of the scientists, so you just Google them up. Okay. Now, including one in the ultraviolet region, right? This is the ultraviolet range, one in the visible, and a lot of them in the infrared range. Okay, so ultraviolet range, visible range, and the infrared range. This is not for every element, this is only for hydrogen. All these scientists were interested in studying the amount of energy or the amount of light that was being released by the hydrogen. Okay, now see. Yeah. So the ultraviolet light has a lower wavelength. It has a higher frequency. Visible light has a less, a little bit low, a higher wavelength, so lower frequency. Okay. So if it's like this, Akshay. If I drop a small stone from a very small height, okay, if the distance that the stone is falling is small, then it will produce less energy, less sound, right? The impact will be less. But if the same stone is being thrown from the Burj Khalifa, okay, from a great distance, that stone could actually create some impact. That the speed of the stone when it is falling down could actually break a window glass of a car, right? So similarly, the when an electron falls to a great extent, like in the case of ground states, it will produce a radiation which has very high energy. Now, in the future, you're going to learn something called here only you're going to learn some this. Okay. Now, there was a scientist called Max Planck. Okay. He was the one who gave the relation between the frequency and the energy of a radiation. He said that if a radiation has a very high frequency, then it has a very high energy also. So, ultraviolet light has very high frequency. Therefore, the energy of the ultraviolet radiation is also very, very large. Clear? So, now we now know that the emission spectrum are produced by atoms that emit photons of light during energy changes. When one excited atom moves to a lower energy state, that is basically when it's an excited atom is not the right word. An excited electron is a right word. When an excited electron inside an atom goes to a lower energy state, it emits radiation. Okay, it emits a radiation in the form of energy it is getting emitted. Now what else is happening? Now we know that the emission spectrum are produced by atoms that emit photons of light during energy changes when one excited atom moves to a lower energy state. This electromagnetic radiation arrives at a discrete energy packet, properly known as quantum of energy. There are discrete packets of energy known as quanta. Now, before Max Planck, people believed that the radiation is nothing but light. Okay, light and various different energy levels. You can have the gamma rays, then you have the cosmic rays, radio frequencies, radio waves. Okay, then you have microwaves. All of these are radiations only. Okay, before Max Planck, people believed that these radiations had a wave-like property. But Max Planck came and said that no, these radiations could also be considered as small packets. Okay, instead of thinking that water is flowing as a river, you are thinking that water is flowing as drops. Like imagine the example of rain. Every single drop of water is not pouring on top of you like a waterfall. It is flowing in one small drops, right? So you can imagine the radiation that is coming from the sky as small packets of quanta. These small packets of quanta, instead of moving as one single unit, these packets of energies having different frequencies, they are carrying this energy in small, small packets called quanta. Okay, understood? Quanta. And the energy that is inside these packets is proportional to the frequency that this light is moving through. Okay, if a light has a higher frequency, then the packets that this light is made up of will contain higher energy levels. Okay, so then you will say that this radiation has high energy. What is quanta? Quanta is the droplets of water that are falling from the sky. Okay, it is similar to droplets of water falling from the sky. From a light source, you can think of light flowing towards us, light moving towards us as small packets of energies called quanta. Clear? Small packets of energies called quanta. Now, the energy packets in the visible region are called photons. Okay, now the light that we can see, the light that we can see, those packets will be called photons. Microwaves cannot be seen, radio waves cannot be seen, so those packets will be called quanta. Because light can be seen by our eyes, we call the packets of light as photons. Clear? Okay. Now, the energy of a photon is linked to its frequency by E is equal to h mu, where h is called the Planck's constant. H is called the, okay. Now, this energy is also equal to the difference in the energy level in the two atomic energy states and after the atomic transition. So we know that there are energy levels around the nucleus of an atom in which these electrons lie. If an electron wants to lie in a certain energy level, it has to maintain that energy. Now we know that the electron has moved from a lower energy state to a higher energy state. Am I right? So when it comes back to its lower energy state, it has to remove this excess energy in the form of radiation. Okay, it has to remove this excess energy in the form of radiation. So you can, by analyzing the radiation that is coming from the atom, you can calculate from which energy level has the electron come. Okay, for example, you are in a train. Okay, you are in a train in India. It took you 3 hours to reach me. By rough calculations, I can say that, oh, you must be coming from Punjab. But it only took you like 20 minutes to reach me. Then I can say that you are only like 10 to 15 kilometers away from me. 15 kilometers away from me because it only took you 15 minutes. So by calculating the time that you came, that was required for you to come here, I was able to calculate your initial position. Similarly, by calculating the amount of energy that was coming from the electron, I could calculate from which energy level it fell. Okay, did it came from the second to the first? Did it came from the third to the second, fourth to the third? Okay, we can calculate the transition that is taking place. Clear? Okay. Now, the exact energy difference in the atomic energy states appear as energies of photons. The transition that took place, the time that was required for you to reach me, I basically use it as an inference for the distance that you are away from me. Similarly, the energy that the photon released, the energy of the photon that was released during this transition was used to calculate the transition energy levels. That is, whether it came from a fourth to the second, from the third to the first. Okay, so I'm giving you side by side examples of real world and the concept that is happening in front of you. Okay, these are not the same things. Okay, photons are not raindrops, but I'm giving you a picture to analyze and imagine. You need to have a picture in your head, okay, for these theories to work. So that's what I'm trying to do here. Now, the constant h is called the Planck's constant, which converts frequencies and wavelengths into their energy equivalent. So basically, if I tell you that a certain radiation has a frequency f, so you can calculate the energy of that radiation by multiplying it with with h to get the corresponding energy level. This is what Planck's equation tells us. Okay, it gives us a corresponding energy level for a certain frequency. And we also know that the speed of light is equal to what? Frequency into wavelength, right? So frequency is equal to c upon lambda. So the same formula can be written as E is equal to h c upon lambda. So wavelength and frequencies of radiation can be used to calculate the energies that are present in it. Okay, the energy of the radiation can be calculated by calculating the frequency or the wavelength of that radiation. Clear? Okay, next. The equation can also be written in terms of wavelength. Using the equation C is equal to mu lambda, mu or F. You guys use F, we use the letter mu. For us, frequency is this. Okay, now where c is the speed of the electromagnetic wave, as E is equal to hc by lambda. Okay, now Akshay, um, can one second. So students, we are going to end this class here. Okay, the next video we will continue from the same exact position. Okay, if you like the way I'm explaining my videos to you, if you like the imaginative ways I'm trying to basically connect the theoretical with the practical, okay, if you like the concept and if you like the way I'm teaching you, please do like, share and subscribe to my channel. Okay, and I'll see you in the next video. Thank you so much.